Most stars in the universe are so small and dim that human eyes can never see them. Yet these quiet objects may outlive almost everything else in existence. Some could continue shining for trillions of years, long after galaxies begin to change beyond recognition. Tonight, we explore the hidden life cycle of red dwarfs, the slow-burning stars that dominate the Milky Way and may shape the future of life itself. Welcome to Relaxing Facts Studio, where science, space, and the universe unfold through calm, immersive documentary storytelling designed to reveal the extraordinary systems hidden behind the night sky we thought we already understood. Small, dim stars fill almost every region of the Milky Way, yet most people never notice them because their light barely reaches Earth without telescopes. These stars are called red dwarfs, and astronomers estimate they make up nearly 70% of all stars in our galaxy. A single red dwarf can shine at less than 1% of the sun's brightness. That matters nearby. Even some of the closest stars to Earth remain completely invisible to the naked eye because their energy output stays extremely low. That low brightness comes from how slowly these stars consume fuel deep inside their cores. Red dwarfs contain far less mass than larger stars, so gravity compresses their interiors with less force, reducing core temperature and slowing nuclear fusion. The process still converts hydrogen into helium, but at a controlled rate that can continue for trillions of years. Giant stars behave very differently. Their stronger gravity creates enormous pressure, causing fusion to accelerate rapidly and burn through fuel in only millions or billions of years. That difference in fuel consumption completely changes how stars populate galaxies over time. Massive stars shine brighter and dominate telescope images, but they die comparatively fast through supernova explosions or stellar collapse. Red dwarfs remain stable for periods longer than the current age of the universe. The contrast is enormous. If stars were compared to light bulbs, giant stars would resemble stadium floodlights that burn intensely and fail early, while red dwarfs behave more like tiny LEDs running continuously for geological timescales. That extreme longevity reshapes the entire stellar population of the Milky Way because old red dwarfs accumulate while massive stars disappear. Over billions of years, galaxies naturally become crowded with these low-mass survivors. Many orbit quietly through nearby space undetected. Even Proxima Centauri, the closest star to our solar system, is a faint red dwarf requiring optical aid to observe. The night sky appears dominated by bright stars, but the galaxy itself is overwhelmingly built from dim ones. Hot gas inside a red dwarf never stays in one place for long because the entire star constantly circulates material between its core and outer layers. Astronomers call this process full convection, and it works almost like boiling water moving through a pot. Fresh hydrogen slowly sinks inward while hotter helium-rich material rises outward. That circulation changes everything. Unlike larger stars, red dwarfs do not trap most of their fuel away from the fusion region, allowing them to use nearly all available hydrogen over extremely long periods. That continuous circulation keeps nuclear fusion remarkably efficient despite the star's low temperature and weak brightness. Inside the core, hydrogen atoms still combine through proton-proton fusion, releasing energy that balances gravity from crushing the star further inward. The reaction proceeds slowly because pressure remains relatively low compared to massive stars. Low pressure matters here. In giant stars, intense compression causes fusion to accelerate dramatically, creating unstable energy output and much faster aging across the stellar interior. That slower fusion rate produces a completely different form of stellar evolution than astronomers observe in stars like the Sun. Larger stars gradually build inactive helium cores that separate from surrounding hydrogen layers, limiting how much fuel remains usable over time. Red dwarfs avoid that problem because convection continuously mixes their interiors together. Almost nothing gets wasted. A typical red dwarf with about 10% of the Sun's mass may survive for several trillion years, far exceeding the universe's current age of roughly 13.8 billion years. That timescale stretches so far into the future that no red dwarf has ever completed its full life cycle since the Big Bang. Every red dwarf ever formed still exists somewhere in the observable universe today. The numbers become difficult to visualize. If Earth's entire geological history were compressed into a single day, many red dwarfs would continue burning steadily for thousands of additional years on that same scale. Their slow hydrogen consumption effectively turns them into the longest living stable objects in cosmic evolution. A red dwarf slowly grows hotter over unimaginable stretches of time because hydrogen fusion gradually changes the composition of the entire star, not just its core. Full convection keeps mixing fresh material inward for trillions of years, allowing helium to spread evenly throughout the interior. As helium concentration rises, the star contracts slightly under gravity, increasing internal temperature and boosting fusion efficiency. The change happens incredibly slowly. Long after galaxies begin fading, some ancient red dwarfs may eventually emit enough energy to appear bluish-white instead of deep red. That theoretical transition creates what astronomers call a blue dwarf, a star that has become hotter and brighter near the end of its hydrogen-burning life. The color shift comes from rising surface temperature, which changes the wavelengths of light escaping the stellar atmosphere. Cooler stars emit more red and infrared radiation, while hotter surfaces radiate shorter blue wavelengths through blackbody radiation. The physics is well understood. What remains unusual is the timescale, because this transformation requires far more time than the universe has existed so far. That delay separates blue dwarfs from other stellar remnants astronomers already observe throughout the Milky Way. Massive stars evolve rapidly into red giants, then collapse into neutron stars, black holes, or white dwarfs within millions or billions of years. Red dwarfs follow a far quieter path. They never become enormous supergiants because their low mass prevents the runaway expansion seen in larger stars. Instead, the star slowly heats, brightens, and eventually exhausts nearly all hydrogen before shrinking into a cooling white dwarf remnant. That final collapse lies so far in the future that no civilization in cosmic history has ever witnessed a true blue dwarf directly. Even the oldest known stars remain far too young for the process to begin naturally. The timeline is almost absurdly large. 1 trillion years is roughly 70 times longer than the current age of the universe, meaning every prediction about blue dwarfs comes from stellar evolution models rather than observation. These stars belong to a future era of cosmology humanity may never physically see. Small planets can orbit surprisingly close to red dwarfs and still maintain temperatures suitable for liquid water because these stars release far less energy than the Sun. Around many red dwarfs, the habitable zone sits closer than Mercury's orbit in our solar system. Distance changes everything. A nearby planet can complete an entire orbit in only a few days while still receiving moderate heat, making red dwarf systems some of the most common locations where astronomers search for potentially habitable exoplanets. That close orbit creates serious environmental challenges because gravity can gradually lock one side of a planet permanently toward the star. Astronomers call this tidal locking, and it may produce extreme temperature differences between the day side and night side. At the same time, young red dwarfs often release powerful stellar flares driven by magnetic reconnection in their atmospheres. Radiation becomes a major problem. Repeated flares can strip planetary atmospheres over time, especially if the planet lacks a strong magnetic field for protection. Those violent conditions seem hostile at first, yet red dwarfs eventually become some of the most stable stars in the universe once their early activity declines. Large stars offer wider habitable zones, but they also burn out comparatively quickly, limiting the time available for biological evolution. Red dwarfs remain steady for trillions of years. That stability may matter more. A civilization orbiting an old red dwarf could theoretically survive through periods of cosmic history long after many brighter stars have already disappeared. That enormous lifespan changes the long-term future of life across the galaxy because most potentially habitable planets may ultimately orbit dim, low-mass stars rather than Sun-like ones. The numbers strongly favor red dwarfs. Since these stars dominate the Milky Way and survive for unimaginable durations, they provide the longest continuous energy source available for planetary systems. If advanced alien civilizations exist far in the future, many astronomers suspect they may emerge around ancient red dwarf stars that continue shining after most of the visible universe has gone dark. Dim red dwarfs may look insignificant from Earth, yet they could become the last enduring lights in the universe, surviving long after brighter stars disappear. Their slow fusion, immense lifespans, and stable energy output may shape the future of planets, galaxies, and perhaps even intelligent life itself. Thanks for watching this episode on Relaxing Facts Studio. If you enjoyed it, please subscribe and turn on notifications so you never miss future documentaries. Share this video on your social media pages, like the video to help more viewers discover the channel, and leave a comment sharing your thoughts. Your support keeps this channel growing and alive.